Okay, we're going to start from page 15 and 저 지금 오는 거야? 제곱미터 지금 창원에서 같이 올라오는 거야? 아, 성은이는 못 받고? 오케이. We're going to start page 15. It's a whole story on correlation functions. So let's assume x and y, which is really a stochastic process, be measured algebraic processes. The covariance function between x and y for any time delay tau is given by this cxy tau is covariance functions. So I keep telling you there are still a few more the definitions are coming, but as you look at very carefully, it's not difficult to understand the definitions and what it does. And today's lecture, when you look at the covariance function and also correlation functions, and when you take the Fourier transform, get the autospectral or power spectral functions or cross spectral functions, as we look through, definitions should be very clear because it's like a Fourier transform pairs and things like that. Here, the covariance function are using the C. That's very typical. CXY, X and Y. That makes, should I would do the cross covariance function in a sense. Auto means the same, the variable X and X, and the cross always mean X and Y, but here the definition we use is covariance functions anyway. So expected value of x minus mu x and y with the time delay tau minus the mu y. And when you plot few pages after, I'm going to give you the sample of correlation function and auto the variance functions for the case of sine functions, sine plus noise with other functions too. Then using that, such a function is very easy to identify the content of the noise and vice versa. As you look at here, then you can open this the bracket here, not the bracket. What do you call this? This is not the parenthesis, this is a parenthesis. But anyway, the bracket, x times y with the time delay tau. So that's, this is same definitions as limit t goes to, approaches to infinity, 1 over t, which is equivalent to 2, the probability density function, and x minus mu x, y, t plus tau minus mu, the same definition here. Then you can open this up. So x times y, x times mu y, mu x times y, the mu x times mu y. So this is the first multiplications here. and then after that x times mu y. So what's the definition of this guy? What do you call the first? Only difference between this and that is what? X minus mu x, y minus mu y. That's missing. It's like in the early part, in chapter 2, we use variance. Okay, variance and mean square value. That kind of the relations, which is the really reference, 0 or the mean value. It's identical relation. What do you call this? This is called R, X, Y, right? Which is called cross correlation function. It's coming next page. And also the next multiplication is x times mu y, right here. Mu y is what? Constant, right? You can take them outside of the integration. Then what's the rest you call? What do you call this? What do you call this without mu y? Yingyu. What do you call that? Just without the mu y. This is equal to mu x. And here, third term is mu x times y, t plus tau. Really doesn't matter. T plus tau is any arbitrary time, right? So here's mu x is a constant, mean value of x. You can take outside of integration. Then if you see it, then without the mu x, what is it? Mu y. So this is mu minus mu y. This is minus mu xy. This is minus mu xy. Then you have 2, right? Minus 2 mu x mu y. And what about this guy? Oh, this is what we did. So that's what the mu x times mu y. And the last term is this. What's the value of this? What's the value of this? What's the integration of 0 to t dt? T over t is 1. So this guy is a 1. So it's a plus mu x mu y. So then covariance is cxy, tau is rxy, tau minus 2 mu x mu y, and the last one is plus mu x mu y. So you have rxy. Tau is time delay, right? So which is minus mu x mu y. This is cross correlation function. This is covariance function. So it has relations here. So so next page it spells out all that. Cxy, rxy minus this guy and that guy. This is a cross correlation function. Cross correlation function. As you look at the cross correlation function, R, X, Y, tau, definition is E, right? X, T, Y, T plus tau. So if I just rewrite for special case, if it's a 0, which is E, xt, y, t. And if this is rxx 0, what do you call this? This is E x t square. This is equal, what do you call this? Mean square value, right? So mean square value, so we use notation psi square. What do you call this? Mean square value. So comparing the sigma square, or you can say psi x, sigma x, what's the difference between mean square and variance? The difference, this guy is E, x minus mu x square. The difference is between this guy and that guy is this is centered around the mean. This is centered around the 0. That's the only difference. The special case is rather than xy covariance, replace y to x, which is cxx, which use the word autocovariance. So I would like to say cxy is cross covariance, but usually just use the name, the covariance. Okay. Cxx, x, x. So cxx tau is equal to, if you just open up all that, is rxx minus mu x squared. So again, open up, another expression is this is autocorrelation functions. Okay. That's about all before getting into the spectral density function, or simply spectral functions. You can tell all that. So after this week, then Monday next week, did you receive a sample midterm exam? No, okay. Higu's grandfather passed away, so that's what I heard this morning. So I'll email you after class. Okay. So he's out in Incheon, in Ganghwa Island is where his grandfather used to live. Okay, so after the exam, I hate to say exam, that's a very good time to review. Okay, it's not much, chapter 1, chapter 2, chapter 3, up to the point I cover up to the coming Friday. I think I will cover them all. Hope. So that's what we're gonna do. Then after that, everything should be clear. Because you will study, right? No? You will study, right? Charu, right? Yeah. And now property a little bit. I talk, now your turn to really derive and write up. Okay, so derive it. So it's a property of correlation function. You can do, last year I think I did it myself, but it's rather simple, so it's no reason. There's no reason not to. Yeah. Maybe I'll do easiest one for you, then you do a little bit more work yourself. So first property. This is a auto, or you say auto correlation function Rxx minus tau is equal to Rxx tau. Such a function Rxx, what do you call? Even function or odd function? Which is even function naturally, right? This is even function. This is even function. So Rxx is even function. And Rxy cross correlation function Rxy minus tau is Ryx tau. It's nothing to do with even functions or other functions. And Ryx, so Ryx, if you write it, how can you say? Ryx tau. If I write this guy, what can you say? Which is y, t, and x, t plus tau. Something like this, which is not the same as, which is e, xt, y, which is not the same. And anybody can visualize this guy? Third property, Rxx is 0, tau is 0, which is e to the x square, t, right? Which is what do you call this? Mean square value. Mean square value is psi x square, you usually call, is equal to the sigma x square plus mu x square. Can you visualize it? How this is equal to this? Anybody cannot visualize it? Visualize it. Don't memorize it, just visualize it. Okay, what I'm gonna do, I said property, I'll do the first property derivation, second, third we have done a long time ago. So then the fourth property, Rxx tau goes to infinity. Then tau goes to this is r xx. Tau goes to infinity. This guy will approach to mu x squared. Nothing to prove. Well, there should be some way to prove it, but it converges into the mu x squared. That's all I can tell. So I want you to mainly, I'll do one, you do one, but this guy, third, is in chapter 2. We have done it already. Very simple. Then sigma x squared, you know the expression. Let's do this first, because that's done already. So sigma x squared is e to the what? X minus mu x squared, which is equal to x squared minus 2 mu xx plus mu x squared. This is equal to x squared minus, this is constant, so e to the x is mu x is minus 2 mu x squared plus mu x squared, and this is equal to e to the x squared minus mu. So my midterm exam is like simple one, not the complex. Then you have to know the basic derivations, okay? And Rxx tau minus tau is equal to Rxx tau. Let's see how I did. For the derivation, I'm going to say this guy. Start from the definition. This definition is what? E to the x t x. I start from the always pure definition. No memorization. So if I write this guy xx minus tau, I replace tau to minus tau, e xt minus tau, then this is equal to, this is earlier time, this is later time. So if you have start from maybe here, this is t, this guy is tau, so this is t plus tau, earlier and later time. So here I can rewrite this guy and say x t minus tau and x t, right? Yeah. So what I'm gonna do? This is any arbitrary time, okay? So I'm gonna simply add t plus tau. How is that sound? Keep adding just the tau, then x t minus tau plus tau. This number manipulation, this is 0. So back to here, and xt plus tau. So this guy is equal to that guy, which is equal to this guy is equal to that guy. It's a symmetric function. So if you have this guy 0, this is tau, negative tau is a symmetry about the vertical axis. And here, this point is Rxx 0. Rxx 0. What is it? Which is equal to psi x squared. And always, this point in the autocorrelation function, this is always the highest point, highest magnitude. Okay. Oh, what about, as you will do, what about the Rxx? If you plot this Rxx of sinusoidal function, Rxx of harmonic function, you can say, harmonic or sine cosine function. Sine cosine function, for example, this is sine cosine function. The Rxx is, as I remember, you can calculate. This is Rxx. This is tau, function of time delay. This is 0. It's harmonic function. This is like xx sine or cosine theta. It's gonna be like this. There is no peak point. There is no peak point like this for sine or cosine. It's all same. They're slightly different. So you can see the waveforms. You can tell, wow, if it's noise contamination is there, then the wave pattern is different. Vice versa. Okay? So you don't need to submit. I hate to tell, submit this, submit that, but sometimes you do. But do this. Derivation shouldn't spend more than 5 minutes. This you don't have to write anything as I did here. You look at it, you should be able to tell. This is convergence. You have to really draw. After you get the function, then you have to really draw the plot the function. Then you can see converge to mu x squared. Okay. So this is another case, just a sample showing Rxy, which is not symmetry, of course, which is could vary all the time. Okay. And if you look at here, this is not the C, this is covariance functions, okay, Cxx. So that's a different scale compared with the Rxx, and this is a Cxx. This is Rxx function. And the value here happen to be 0. In this case, approaches to the mu x squared, but this is approaches to 0. Today, some assignment which you don't need to turn in, but try out. And this cross correlation function, I have done this by solving for discriminant. Discriminant, you remember last week? Discriminant in the process to get that, then you have all that to get the discriminant. But how, I'll just give you a tip, then couple inequality you have to work on, which is cross correlation, the inequality problem, which both are very close to each other and has some meaning, quite a meaning, as you will see. The middle one is correlation coefficient function. When you put the tau in there, put the name functions, okay? This is tau domain function, rho xy, correlation coefficient. When you put the tau, then it's a function. Correlation coefficient function. Okay? So first one, this relationship, I want you to start. Some of the students last year, or some year before, how did you get this equation to get the result? There are tons of mathematicians, they try almost anything. So this is just start. Without knowing this, of course, not easy. I would rather put this guy. Can I say this is greater or equal to 0? A and B are the real constant, non-zero. It could be 0, then if the whole thing is equal to 0. Now you have to expand this. You have to expand this, get the quadratic equation. Remember the quadratic equations we developed last week? Quadratic equation. So you remember the A over B square quadratic equation of A over B. Then determine the discriminant. So quad equation to have the root greater or equal to 0. Remember, this has nothing to do with this. I did. So remember this function of x, right? So root, right? Root means when you set this guy as first to get the root, something like this. So inside here has to be less than or equal to 0. Otherwise, you are not going to get you will get the root. So So you have to have over here b squared minus 4ac has to be less than or equal to 0. I want you to do that. You will do it this time. 판별식. This is discriminant. So in the process, apply this into here. Then you will get that. Try out. And if you look at okay, this guy, let me see, this guy is out. This guy should be there. And if you over here, when you look at the covariance functions here and correlation function, there is a difference, I said. The difference is one Rxx, R is centered at 0. C is centered at the mean. Okay? So if you in the process, when you you will get the, of course, R, X, Y, tau is, oh, sorry, tau is less than that square root of R, X, X, 0, R, Y, 0. Top, we can derive it. And C is related, you replace xt, replace xt by xt minus mu x. What I'm trying to do, shift the means, right? And yt as yt minus mu y. Okay? I want you to think about it. Then you will get the second relationship. Take a look at it, okay? Which is not bad. And the correlation function, absolute, is less than equal to 1. Then you can tell the range. We have done this similar correlation coefficient before. It's between -1 to 1, similar correlation function. I start to giving you a little bit work to do in your leisure time. I think it's good for you. And STX guys are busy, so busy, and right now I don't know what to do, but do your best and see me, then we can talk. And my note is pretty thorough, and Hikyu has a few reference books, and you can take a look at. I fully understand how difficult your life will be, but remember, have a joy, because you will end up having what degree? Master's degree. Yes. That's really nice, isn't it? Now, the spectral function. How many are exposed on spectral function? Spectral density function. How many power spectral density function? Yungyu, right? Yungyu, right? Am I pointing you? Yungyu, have you heard the spectral density function? Yungyu. Yungyu is another guy. How come your names are so close to each other? Sorry. Yunsong. Yeah. Yunsong, you heard about the spectral density function? What is it? Just you feel, whatever. Anything. Okay. How about Charo? Jeju person. Yeah. How about Sangwon?
I think it's kind of density function using spectrum.
Yeah. How many heard the name Yochin? Everybody knows. I'm just kidding you, okay? Spectral density function. Simply speaking, spectral density function is a Fourier transform of correlation function. So simple. Spectral density function, I always use f to simplify the derivation. You can use, of course, omega, which is a circular natural frequency, radian per second. F is hertz, cycle per second. And of course, which has that relationship. Some textbook, of course, use mostly omega. Then you have to use 2 pi as a dividers and all that. But if you use f, it's just the constant, multiplication of constant. Everything fits as is, so you don't need to remember anything. So I use f, and that's using always f, expression using f. So here, you know the Fourier spectral infinite r, x, y, tau, which is time domain function, e to the minus j 2 pi f tau theta. xy, which is a cross spectral density function, xy. And if you replace y to x, which is called auto spectral density function, sometimes engineers are using the name what? Power spectral density function. power spectral density function. And electrical engineering people, they use autospectral density function. It's identical things, okay? And if you open this up, if you open up e to the minus j theta, I can express this guy as a cosine theta minus j sine theta. So first term, if you look at just expanding this guy, first one is cosine 2 pi f tau theta, right? And the second term is j, this is minus sine 2 pi f tau theta. And also, you can tell here, you can say it's an even function or odd function, but if you talk about the auto spectral density function, then you can really tell it's important. I'm not sure whether I cover in the next page or not. I cover next page, so I'll wait until next page. It has Sxy, this is real part, and this is imaginary part. And this is cosine and sine, and phase difference is 90 degrees. Then you can have complex plane. So Sxy can be expressed as also magnitude e to the minus j phi theta xy. Can you see? Very straightforward. So you have this is real part, this is the imaginary part. Usually that's minus, so which is theta xy. So this portion is cosine function, cosine value, and this is sine value. So this is, I'm going to say, real part. This is imaginary part S. So theta xy angle is what? Arc tangent, right? Arc tangent of what? SR over SI. So you can always get the angle and the magnitude. So Rxy by definition is this. It's all clear. Sxy. Now Sxx and Sxy is different. When you compute Rxy tau, this is I said done before FFT came out. Then you can have always Sxy. This is in frequency domain. So this is a frequency. Transform into the frequency domain. Then of course, from here you can take inverse Fourier transform. Then you can throw back into the time domain. Okay? This is what happened, right? But Rxx or RYY. Of course, this is time domain. Okay. If you throw into the frequency domain, SXX, SYY, of course in the frequency domain, you will never be able to go back to time domain one way, because you do not have here the angle, phase difference information. No info of phase. What does it mean? How it happened? That's what you're going to hear. Over here. So you just expand the real part. If you expand this, there should have another term. That term will be like this. That term will be, that's a minus, right? It's a minus J integration minus infinity to infinity R XX sine 2 pi f tau d tau, right? Look at me. This guy is even function or odd function? Even function or odd function? Even function. Is sine function even function or odd function? Louder. Huh? I'm talking time domain, tau domain. This is sine function, right? Sine goes like this, right? Sine goes like that, right? What does it mean, odd function? Some function of tau becomes minus f minus tau, then that's odd function. Simply speaking, you fold it and fold it again. So that's odd function. In other words, one cycle here from here to here, here to here. You integrate, the result is 0, right? Result is 0. This is odd function. Even function times odd function is odd function. When you integrate minus to plus, zap 0. This goes same area, right? So then this guy is 0, right? Complex part not available is 0. Then you have only the real part. When you have a real part, you can't go back. Once you marry forever. That's what it should be. 한성, 아니야. 윤성, 그지? So that's what. Alright, I'll stop here. Then I'll see you tonight, right? 6 o'clock to 7 o'clock. No prayer, right? Gusto? Tonight, no prayer. Okay, I'll see you.